So yeah, thanks for coming. I know end of the day's interesting to see who actually shows up. I'm Jeff Vestal, so I work at Elastic. I've been there 5.5 years. I used to work in trading firms. I used to work at E-Trade before on the engineering side and operations side, so I've done a lot of stuff. These days I tend to focus on search and Gen AI and all the buzzwords that entails. A couple quick, let's say, housekeeping slides. So there's the app. If you haven't downloaded it, it's nice. You can do the QR code. And then I have 2 Elastic plugs as well, just to get it out. So if you're familiar with Elastic, if you're not, you may have seen our marketing blogs over the years, and they're marketing great. But if you're a developer and you're interested more in the technical content, if you go to Search Labs, so elastic.co/search-labs, these are where our real technical content is. It's written by the engineering team. I'm in the field, so field team, developers. Again, really technically focused, not just kind of marketing things. There's also then the associated GitHub. So there's full applications you can clone and download and get up and running real fast, Jupyter notebooks, all that fun stuff. And then a even more personal plug. My boss and I, I guess at the end of last year, we wrote a book on using operationalizing vector search for Elastic. So if you're interested in this, it's from the operational perspective, right? So if actually using things, it's not the ML research books. There's other better ones on that. But if you want to actually use this stuff, you can check that out. All right. With that said, so I know there's probably a wide range of experience here. So we're going to do a couple little laying the foundation things. So Lexical 101. So with Elastic, when you do term-based search, these are the things we've been doing for a long time. You go through your input, it goes through tokenizers, analyzers, and things like that to clean it up and break it apart. And then we store it in the inverted index. So for example, if your input is jumping foxes, goes through the analyzers and other components, and you wind up with jump fox, which then gets broken up into jump or fox, and then we store it in the inverted index. So this is things, again, we've been doing, I think Elastic is 12 or 13 years at this point, but it's based on decades of research well beyond Elastic, and it continues to actually be tuned and optimized. So if you take, for example, 2 documents, you have the quick brown fox jumps over the lazy dog, and you have dogs can jump dogs, whatever that means. When we process it, we store it in the inverted index. And so you have the column, so you have your terms, brown and dog. You have the doc frequency, how many documents that appears in. And then you have the postings field, which has things like, again, the doc ID, term frequency, positions. And so this is how we can search petabyte scale at millisecond speed, because you're not doing a full text search over all the actual documents. You're going to that inverted index in the back and just looking for the word and then jumping to the doc. Allows it to work pretty fast. And because of that need, there is the necessary complexity, but it all is optimized, again, for speed and efficiency, and it works really well. That was the shortest version of lexical search I could ever make. So again, the reason we were kind of focused on that is then to show the opposing view, or the newer view, I guess, of semantical search. So if anyone is really deep in the field on this, don't jump on me that I put only 2. There are definitely many subtypes of models, but we're going to talk about 2 high general types of vector models today. So dense vector models are the ones that you almost certainly use if you've used vector search or you're talking to chat apps. This is what today vector search uses for the vast majority. And on the output side, you have just this array of floats on the left side. Sparse vectors are, I'm not going to say newer, but they're starting to become a little more common. And the middle layers you'll see are the same, but the output is a token and a weight. And so I mentioned this because when we're talking about sparse vectors here, we're talking about semantic sparse vectors. So one example is ELSER model. That's Elastic's Elastic Learn Sparse Encoder. We'll talk a little bit more about the details of it in a second. But it's important to know that these models share the kind of beginning and middle same architecture. So they're both based on transformer models. For example, BERT. The middle layers use the semantic relationship and the attention mechanism. And so this is how when you insert, bring in a text field or something, all these middle layers learn their relationships on how words are formed, their importance of their position, how they relate to other words, and you're basically generating the model's understanding of what the meaning is of the document. And this is then where they differ. So dense vectors, then again, are dense. One reason we call them dense is because they output a fixed number of dimensions every single time. So you'll see things like 786 or 1536 dimensions, 768. So every time a model that outputs 768 dimensions, it always outputs that. If you think of them kind of as slots, every slot is filled, every slot has a value that's important. Conversely, then sparse vectors are sparse because they have these dictionaries of potentially hundreds of thousands of words, and the vast majority of those values are 0 because they're not relevant to whatever your input was. So it's sparsely populated. And in this case, we output, again, that token and the weight. Dense vectors, for the vast majority, are the vector you get is the representation of the whole input. So the output vector represents a sentence, a paragraph, whatever. That's its representation of that whole input. It's not every single token has its own input. Now there are special, you can't see it behind me, little special corner called Colbert, and there's a couple other ones that have multi-dimension almost, things like that. We're not talking about that today, but sparse vectors, on the other hand, do what we call late interaction. So it goes through that model, and then the scoring, token-based, happens later on at the end. So when we output the token, we weigh the importance of it. So typical semantical search was that you have the meaning. You're trying to get to the meaning of what the document is. You have a model in the index. So jumping foxes goes through the ML model and then goes to the index. And in this case, we're going to store vectors. So these have been around, again, for a long time. Been doing research. It's been mostly in the research academia field, though. It's only been the last couple of years that they kind of broke out, and with the BERT model and things like that, where they've kind of changed everything we've been doing lately. But they're usually tuned by machines running scripts and reinforcement learning, things like that. There's some human in the loop at points there, but vast majority is automatic tuning. So when you have now this document, the quick brown fox, it goes to the ML model, and if it's a dense vector model, you store the dense vector. So we store, again, the ordinal value, the vector itself, but then to make it search performant, we store the neighbors in the graph. So we store, we generate what's called the HNSW graph, the hierarchical navigable small worlds graph. You can think of it, the best way I can think of it is if you're on like Google Maps, you open up Google Earth and you say, okay, I'm going to Sears Tower. It's called the Sears Tower. And I live nearby, so I want to see where I am. So I'm it, and I zoom in, and I want to get rid of things that aren't relevant to my search. I want to find where this location is. Then I zoom in again, and I can quickly drop, and I can take out a whole nother blast because I'm only looking at Chicago. Then I'm looking, I took Metro down, so I'm looking within a couple blocks of Metro. This way, with the hierarchical navigable small worlds graph, you're able to quickly traverse these graphs and find nearest neighbors. So instead of matching keywords, you're looking for what are the nearest semantically relevant documents, and there's a lot of math involved. So what's in a vector? Kind of whatever the model thinks it is. This is where the training and tuning comes into play. There's these foundational models, and then you can do fine tuning of them for specific use cases. They're generally trained on document and query pairs. Some of the new models even have the ability to tweak what they're going to do. So this one's from Cohere, where depending on if you tell it if it's a search document or a search query document, it'll actually output differently because it has kind of internal tuning for which way you're going to use it. But vectors are an approximation. They're not the exact thing as matching individual keywords. You're always matching the model's interpretation of what the input is. Okay. With that said, we're going to look at ELSER a little bit, the sparse vector model. So sparse vector models, as I mentioned, is based on, our model is based on a paper called Splayed that came out last year. It's a model designed to kind of fix some of the limitations of dense vectors. One of those is for dense vectors, at least when you're using things like Lucene, where you're generating these graphs. For the search to be performant, you have to store it in memory. It's expensive off-heap memory. Works really well, it's extremely fast, but if you have hundreds and hundreds of millions of vectors, you're going to have a lot of off-heap RAM. So we can use the ability of the inverted index, which uses much less RAM, and output those tokens and store them in this. ELSER right now is version 2. It is English only, but it works really, really well at what we call out-of-domain learning. So it's not fine-tuned for, say, a legal data set or a medical data set. I kind of think of it as if it's an English document that any normal person can read and understand, ELSER is going to be great at it. It does output, again, those tokens. I'll point out real quick, just in case you're curious, you'll see like hash and then OID. That's where the internal dictionary didn't have, for whatever we're reading, the word droid, so it had to split it. So that's just kind of its marking that these are two. So text expansion, where people get into trouble with sparse vectors in general, ELSER, SPLADE, whatever, is that they think it's just kind of like an auto-synonym machine because we output tokens that look like words, and they are words usually. But there is that neural network expansion layer. So it is important to understand that there is a encoded meaning in the way that these tokens get generated. But you go through your first layer, internal layers, and then we do what's called token expansion. So the tokens that are input, we then find which tokens can be expanded out, similar to synonyms, but not the same. And then we store those, and then the weights are added in. So how important these individual tokens are now to the input. And then at query time, you do the same thing. So you run the input through the model, you generate weights, and then the search phase looks for matches. And then we do some super complicated math. No, it's pretty simple math. Add it up, and that's your score. And this, again, one of the big advantages of sparse vectors is that you're using the inverted index, so you're faster and less memory is required. Again, it works really well on our, all the standard benchmarks and everything out there. But there is a query problem we have with this. Ben's one of our ML engineers who I stole a couple of the next slide from. So even if you're not a search engineer or search expert, you should probably figure that when we do token expansion matching, if I tell you that we're doing 30 to 50 should clauses, that seems like a lot of should clauses for any query. Most, lexical BM25 search you're doing, you don't have 25 to 30 individual tokens in there. You're doing much smaller. And you can see on this chart that has no labels, sorry about that along the x-axis you have basically all the tokens that are across. So the purple one is a lexical search and kind of the frequency across of all the documents potentially. They're not all bunched up, and a lot of them are not relevant to an input. Whereas semantic search, like with ELSER, the red one, because you're doing this kind of token expansion, most of the documents have similar tokens. With BM25, for example, when you're doing a lexical search, if a word appears in every single document or the vast majority of the documents, BM25 will score that lower because it's probably not super important. So we do inverse document frequency, that's the orange line. All this chart that is just crazy drawing is trying to say that ELSER and sparse vectors don't pay attention to things like how frequency of the term. All the terms are weighted equally important. And because we have so many terms, if you just run it straight out of the box, even though you're now getting a semantic search, which is great because it allows people to do natural language, you do then pay a penalty on speed, which isn't great. So what can we do about this? Well, we can just drop a bunch of tokens. You might think I'm kidding, but actually it works pretty well. So we have these two arguments, token frequency ratio and token weight. And these allow you to tune the kind of lower weighted ones that aren't super important, and you can drop those off. And what we've actually found is, so the control row with max 1 disabled is the regular one without it pruned, and then the pruned row is dropping a certain percent of tokens. By dropping the lower weighted ones, you can speed it up between 3x and 7x and get pretty close to normal BM25 search, and recall is almost unaffected. Sometimes it's a little better, sometimes a little worse, but it depends on your data set, but it's largely unaffected. So you get, again, that semantic search that you can use for RAG, which we're going to get to, and then all a great speed up. Okay, a couple other things we're going to do that we're going to use when I show the RAG app that we're going to build. to make things easy, these things are all things to make things easier. So when you're connecting, generating embeddings, or you're doing chat completion or things like this, you have to, connect to models in some way. So one way we can do is use an Inference API endpoint. You can then create an endpoint that connects to either a model running locally in Elastic. You can connect to your favorite embedding service of choice, and then you just have a nice one endpoint that you hit. You can use this at index time or query time, or since it is an endpoint, you can just programmatically hit it. This is nice when you have, again, if you're developers or developers, other people are going to use that data set, you don't have to give them, which embedding model individual they have to use, what's the key to this model and everything. If it's an external service, you just tell them the endpoint service, and then they can connect. And if they're already using Elastic for data, it's all kind of in the same place. Again, nothing super complicated here. You hit the endpoint. It then passes the request to the external service. There's some retry logic and buffering and things like that. Bulk calls, and then we will return it for you. So I've been doing things with vector search and RAG since a couple of years now. And if I was giving this talk a year ago even, we would have gone through a whole thing on how complicated it can be to set up, and tuning dense vector search can be a real pain. Now it still can be, but what we've learned over the last year from real users' experience is a lot of kind of sane defaults that are nice to get up and running. If all you want to do is get something running quickly, kind of have a not weird data set, or even if you just want to POC things, we want to make it easy for you to get up. You want to make a couple API calls, you're up and running. So we have now, we call it the semantic text field. It does automatic chunking and will generate vectors for you. Again, it's kind of these sane defaults where we have, right now there's one chunking methodology. There will be more where you can do it. You don't have to, you specify, it's part of the field mapping. Sorry, I'll come back to that insane slide in a sec. You specify your Inference API endpoint as part of the field mapping. So if you've ever set this up before with us or whichever service, usually every time you make a call, you have to know your model ID. It's kind of a pain, especially when you have to tell other people, or if you change the backend model. By doing it this way, only at creation time of your index where you're going to store the documents, you link it to an embedding service, either locally or externally. And then every other time after that, whether you're querying or you're indexing documents, you use it like every other field. It's kind of like when you use, keyword search, BM25. I don't have to specify, BM25 model in there anywhere. I don't even know where it is. I just use it and it works well out of the box. As I mentioned, we do automatic chunking. There's the first one they got out is 250 word chunks with 100 overlap. The way I explain Elastic to people who might not be familiar with it is our engineering team like to make things embedded and into the product as much as possible. We put it at Lucene layer usually, where that's our underlying library technology, and then we build it into Elastic. And the reason we do it this way is we want it to work with all our features and functionality, not just be like a bolted on part that's kind of a pain to use and kind of works, kind of doesn't. So because of that, what we'll do is we'll release something that works well, but then you have this list of feature requests over here. That's great. I mean, this is one way to do chunking, but we want to do a lot more. So this is just an example where 250 chunks with 100 overlap, it might not be optimal for everyone. It's a good kind of starting point. I know the next one that's coming out, they're going to do sentence chunking. So you specify how many sentences you put together. You can say, do you want chunking or overlap or not? The reason to do overlapping, if you're not familiar, so if I have these chunks 3 and 4, since I'm not doing anything clever, like actually finding where the paragraph boundary is or where this, whatever topic I'm talking about, I just find the words and I'm breaking on them. It's almost certain that these 2 chunks were talking about the same thing. So you want to kind of be able to pull some meaning from the previous or surrounding chunks into it, because you're matching on what does the chunk mean. So by pulling in some of the surrounding, meaning, for lack of a better term, it kind of tends to get better results. Cool. All right. So finally get to RAG, which is in my title. See. Now, I'm going to assume everyone has been seeing RAG around, in 1,000 different ways. I know there's like 5 other talks or 3 other talks about it, which is great. I'm glad to see people are using it. This is my very quick overview for people who aren't familiar. You're the happy smiley guy up there, and we have a chat application where humans interacting with it. So we're going to go counterclockwise today. So the user asks a question. We have some code layer, whatever you want to write your code in, and we want to retrieve some documents. So the little app I'm going to show in a few minutes, it has a restaurant review, kind of like Yelp, but some open source data set. And if I want to see where's the tastiest pizza around, I'll ask my question, and I want to retrieve contextual documents. I want to find documents perhaps that are based on reviews that are in the last year. I want to find places that are within a half mile of here, of the Search Tower, because I don't want to go drive out somewhere far. And you can use semantic search, you can use lexical search, you can combine them together, doing something called reciprocal rank fusion. That's where you run 2 searches, semantic search and lexical search, and then based on the rank that they come back in, there's a little formula, it's pretty straightforward. We rank the results together. This is when you have a data set or a users where sometimes they might ask questions that are just keyword based. People have been kind of trained for decades to just play the keyword game where I'm like, what keywords are in this document I want? Other people are starting to get used to asking questions naturally. But if I know a very specific keyword that's in my document, that's going to hit far better than just kind of trying to describe it. So anyways, that's how you can combine the results together. So that's the retrieval part. Then we return the documents to the app, whatever your middleware app is, or your backend, and we create a prompt. So this is the augmented part. So when you're interacting with LLMs, they're all just taking text input to explain what's going on or tell them what to do. So we take this input and you can get as super creative as you want with these, but the basic foundations of it is you say, okay, the user is asking this question, you give them the question, use the information we provide because the answers are somewhere in this document, and usually you're going to say something around the lines of, don't use your training to come up with the answer yourself because models are going to just predict out the next token, whether it's actually the right answer or not. So if it has just finished training on restaurants yesterday, it's probably going to be pretty good. But if I'm looking for reviews and it's a little older, you don't want it just making up answers. So generally, if you tell it to only use the documents you provide and not make up an answer, you have a higher chance of it not hallucinating. So that's the augmented part. You kind of tell it what to do. And then generation is obviously the chat model generating an answer. And then we pass it back to the user. And hopefully, it all works out well. A couple little, I don't want to say advanced, but different and less common things you can do when you're thinking about RAG applications. One of them is generative caching. Now, there's a couple different generative caching things. The one I'm going to talk about is generating, I'm going to do this in reverse order. Caching the responses from an LLM. So where this is really useful is things like knowledge-based or document stores. So if you have users asking questions about like, how do I do something for your company? Or it's an internal thing on how does some process work, right? And you have kind of the top 100, 1,000, 200, whatever your amount is, but the vast majority of your questions are these people asking these questions over and over. What you can do is store those answers. So I'll kind of walk through this workflow. It's a little weird, but so the first time you ask a question, let's say the cache is empty. Your application queries Elastic, there's nothing in there, so it gets back no hit. You go the normal RAG route. You get some contextual documents, you build your prompt, you pass it to the LLM, you get back your answer, you send it back up to the user, and hopefully they're happy. What you do in parallel then is the bottom in here, send the prompt. So I'm going to store the generated prompt in text. I'm going to store the user's question in text, but I'm going to generate a dense vector for the user's question. The reason I'm going to do this is then I'm going to run similarity search, because if I ask everyone in this room to ask a chatbot, where's the best pizza place, in your own words, if everyone asks basically the exact same thing, we're going to have, I don't know how many people are in there, let's say 50 different slightly variations on how that is phrased. So you can use semantic search, approximate nearest neighbor search, to find questions that are semantically similar. Now, because approximate nearest neighbor is approximate and it's the nearest neighbor, if someone asks something completely off the wall, it will, vector search will return the nearest neighbor. So you can control kind of the closeness of the question by a similarity parameter, and you can tune that. But essentially, if the next person comes around and asks basically the same question, and if it's close enough, this first one is going to do it's up there, for semantically cached answers based on the user's question. If that's a close enough match, I just return my previously generated answer back to the user. So to the user, it seems like the LLM generated the answer. Because it did, it just happened to do it sometime in the past. And so reasons for doing this, as I mentioned, it works really well in some scenarios, definitely not all scenarios, some keep in mind. Increased response speed, even if you're using an extremely fast LLM, GPT-4o, right, it's pretty quick. Returning a document from your vector database is always going to be faster than going the chat route. So you get faster responses, reduced token costs. All this stuff costs money. If you're using a hosted service, certainly you're paying token costs. If you're using a self-hosted one, you're paying GPUs and spikes and all that stuff. The other thing you can do is kind of have your pre-vetted answers. Even if you use all the prompting techniques in the world, sometimes the LLMs go off the rails a little bit, and we've all seen where like car dealers are giving away free cars and stuff, right? It'd be nice to pre-vet some of these answers. So again, if you had 100 or 200 top questions that you want to answer, you can sit down and generate the answers, or you can just type them up and it looks like a generated answer, but then you still allow for those kind of less common questions to be run. So a lot of different uses for it, something to keep in mind. And then two other ways you can use the LLM to help out your RAG app is using it for, we'll zoom, using it to generate queries for you and then generate the conversation memory. So the first thing you can do is have it generate the query to Elasticsearch, your vector data store, for it. The reasons for doing this is generally what you're going to do when you're querying for contextual documents, you're going to template out your query. You have a query or maybe two that you want, you print up and you fill in the keywords that the users ask, but you can almost always create a more custom query and get more relevant documents if based on what the user's asking, maybe based on where they are, time and things like this. So instead of, obviously a human's not going to do this, what you can do is you can pass first a prompt to the LLM and say, again, the user's asking this question, this is the index or multiple indices that are available. These are the relevant fields. You can give it examples of queries if it needs, like this is a lexical, this is a hybrid, this is one using aggregations, blah, 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 like all the filters. The models are pretty good at generating these more tuned query for it. And then you get that back and you do the normal RAG approach. You take that query, you get contextual documents and you pass it back. The other thing you can build in, and there's lots of different ways to do this, is updating memory. So we're all kind of used to using, ChatGPT and all the other services that are out there now. And when you're talking to these models, it kind of seems like they have a memory of what's going on. You can say, what's the best pizza place? And you can say, what time is it open? Like I'm not specifying a specific, I'm just saying it, right? And that's how normal language works. You remember a little bit and then I probably forget. But the way this really works is the models aren't updating in real time. You have to pass the memory of the conversation to the model in the prompt. It's something the users generally never see. But to do that, if you have a short conversation, it's usually not a big deal. But if they're talking back and forth for a while, eventually you're going to hit the model's context window. So this is the amount of tokens, or input that the model can handle at once. Everything outside of that, it either is going to drop it or throw an error, or whichever way it's set up. So one thing we've kind of been playing with is you have it summarize a conversation. So for example, if I'm talking to one of you, the most recent 2 or 3 back and forths are, I'm probably going to ask something about that. Like I'll ask you a follow-up right away to something you asked. And so you might want to keep those 2 or 3 interactions verbose. Like I want to store them exactly, so I put them in an array or a dictionary. But then everything after that, it's important, but it kind of trails off in importance. So you can ask the LLM, hey, this is everything we've talked about so far. I want you to create a summary that the LLM, is going to use as follow-up. You can tell it things like, the user is never going to see this, so it doesn't have to be nice, complete sentences. Just make it as compact and efficient as possible. And you give it a window, right? Like you have 300 characters, pick your whatever you want. And then every time you make a call, you pass back the answer, you ask the LLM to update it. Again, lots of approaches to this, but this is one way you can kind of keep having that back and forth and allow your users to ask follow-up questions about the conversation. Okay. Talked for a while. So I do have a short demo, and then we'll do some questions and answers. I say this all the time, but like I'm not a big slide person, but then I get stuck with 51 slides. So sorry. Okay. The code's not super important here. What we're going to do is this bigger. Okay. I'm going to do that restaurant review thing I said. So I need to clean up some things just to make sure. Views. Me trying to prove it's not all can. And delete. So I'm deleting the index. I'm deleting the data view. That just lets you look at the document. I'm going to delete the endpoint to generate embeddings. Delete the endpoint to talk to, in this case, Azure OpenAI, where we have our tenant. Okay, so we talked about some of this in all the slide build-up I was doing. The first thing I want to do is generate a Inference API endpoint so I can generate these sparse vector or sparse embedding tokens. I specify that it's ELSER and allocations and number of threads. These are just resources that we're going to give to the deployment. Allocations are essentially how many concurrent requests can I do at a time, and then number of threads is number of threads per allocation. So of course we're changing the API, so you get a little warning there, or notice. But what this has done in the background is it's automatically deployed my model for me. I have a new deployment set up, and now I have an endpoint called my ELSER endpoint. Great, we'll test that in a second. Next thing I want to do is set up an Inference API to talk to, again, Azure OpenAI in this case, where I'm going to have my chat completion. So we'll test. So there's my model, or endpoint rather. Here's my model. All I'm looking for here is that it's deployed on some node. I don't care what node, serverless. I'm going to then test generating some embeddings. So again, I like to ask ridiculous questions to LLMs to entertain myself. How many ducks? So this one is generating the embeddings that I could store. And as you can see, there's the tokens, ducks, football, mall. I must have got, oh yeah, mallard, field duck. Anyways, so we're storing those. And then the chat completion that's running, I can ask it, again, just to test that it's working. So it's it's passing the call to OpenAI, and it's making it do this. To me, it's entertaining to use like the most powerful tools we have available to do ridiculous things. So approximately 57,000 ducks can fit. Interestingly, once in a while I get 26,000. I don't know. It's the same model, but same question. Okay, so we have set up our API endpoints, and we're ready to roll. What I'm going to do is go and upload. It's not what I want to do. No, I changed it. I'm in serverless, and we push to serverless all the time. So I think Monday is push day. Let's see what happens. Okay. I have a small restaurant review. Again, this is super small, just for the rank. So what I'm doing now is, uploading this CSV file. You can do PDFs or anything else you want. I'm going to, so what this does is it just kind of analyzes your data. You can see distributions, things like that. If you're not familiar with what you're working with, it's helpful. But I'm going to hit import. I'm going to call it restaurant reviews. I'm going to go to advanced. This is where I can add my semantic text. So I want to run semantic queries on reviews so I can ask things about pizza. And then you can see I have my inference service that I previously set up. So if I add that, if I look down at mappings, you'll see I have my new field, review semantic. It's a semantic text field and it points to that. So that's all that has to happen. I'll hit import. Again, if you wanted to change things like, how to change that? Doesn't matter. I'm not gonna use it. But you can update your mapping as you want. It's going to upload the data, and it's kind of, this part is, again, we're indexing the document, we're automatically chunking it into small chunks, and we're generating, in this case, sparse embeddings for every one of those chunks. There's always one failure with this data set because I haven't fixed it, but then you can go on and start using it. You can go to Playground. So Playground is, you may have seen other playgrounds that are kind of similar, right? Where it's kind of your RAG testing ground. You can, since we created the service, you can connect to different models. I'm going to leave it as 4, and I can ask it again. So we're passing it, and then we're getting back. So the reason, one of the things you can do on Playground is, again, we're testing like the documents that come back. So we'll show you what are the contextual documents that we're getting back. Let's talk about pizza in here, obviously. You can see the scores and how they were passed. So these are the documents that then we would pass to the LLM to kind of ground the model and say, use these documents as part of your response to us. The Playground lets you do other things where you can change number of documents to send if you have a different contextual field, but also allows you to change the query. So right now I'm querying that review semantic, but if I had multiple fields that were relevant, you can turn them on. So maybe I wanted to query the review and the restaurant name, looking for things like that. You can go ahead and change like that, and basically just play around and see which works. But you can also then change it. Again, if you haven't worked with RAGs or LLM a lot, so there's the user part of the prompt that tells the LLM like what's the user's asking, but then you can provide instructions or system instructions on how the model should behave. These are really useful when you want to say how it should behave, who it's talking to. Is it talking to an executive, or is it talking to a developer? Those are two vastly different answers that you probably want to give. You can tell it things to talk about, not talk about. If I regenerate this, now it'll say, it's looking for tasty pizza, and it's kind of piratey talk. But you want to do something more useful with your application. So once you're kind of happy with what's going on here, we can then auto-generate some code for you. So in this case, it's Python code, and you could take this as is and run it. You'd have a base kind of functional app that you could build out. It talks about here's where you create the prompt. Interestingly, with the prompt, for example, I put in a pilot who loves to talk about gold, but we also put in, again, these are some same things where you're kind of adding in information that our developers thought were useful. Feel free to use them, feel free to delete them, and then generate the response, and so on. The only thing I actually want to use today for this is the query. Copy that, I go to VS Code. So I'll show a couple of things in here. This is a Python backend running fast API, and then a React front end. I am not a front end developer, nor am I good at it. It's something I'm working on, so you're going to be blown away by the front end in a second. Real quick, I'll show this first. I'll start it. Running. Host, restart this. Okay. It's not the worst I've seen, but okay. Where can I I'm not doing streaming, so there's going to be a delay in the answer coming back. Usually you want to implement streaming so it looks like the thing's typing at you, you don't have the thing. But again, you're going to get back then, based on information provided, an answer. There's a lot of things we could tune up here. Obviously, it's trying to send me Markdown, but I'm not printing it in Markdown. It's just a short demo app. What's the rating of the first restaurant? Sometimes it works, doesn't. Usually it gives me an answer. What I wanted to show was, if I ask enough questions, this is where streaming comes into play. It makes it a much better demo. Where can I? Just getting a couple interactions so then I can show the memory thing. But again, every time we're making a call here or typing a question, it's doing a couple of things. It's querying Elasticsearch to find documents that are semantically similar. I'm also running the history update every time. Certainly things could be sped up, but in doing this. And then if I ask something like the duck question, I'll see if it gives me an answer. Okay, good, it worked. You want to have some guardrails around it. Don't let it talk about crazy stuff. There's obviously real advanced ways to do this, but just telling it to focus on one thing is the best. Sorry, going verbose. One thing I wanted to show, that history, this is returning all the information that it's doing. Bigger. Sorry, I can't really make it bigger. But when I ask the question, it's going through and returning the documents, and then find summary. So when I ask the summary question, it was printing it out earlier, but I'll show you again. When I'm trying to ask it the question, I'm telling it, you're a conversation specializing in restaurants. Summarize the conversation, prioritize the mention, and then you kind of have this, you're telling it almost the spec that you want it to write in. So I want the summary, I want the key restaurants, relevant details and topics. So every time I go through the conversation, I'm making this call behind the scenes and continually building a history update. So yeah, that's my talk for the last part. I'm happy to answer questions. Again, I'll mention that if you're interested in this, more information, and you want to read and not listen to me talk, if you go to Search Labs, I'll leave this up here while I answer questions. Again, all these, I wrote this one. There's Jupyter Notebooks, sample apps, and all those things to kind of help you get more information up and running and just general information. So, but yeah, thanks for everyone for coming, and enjoy your time.